Hello, welcome to the presentation of my algorithms course homework 7. In this homework I will solve a problem related to depth-first search algorithm on directed or undirected graphs. So now let's start with a basic practice question on depth-first search. Okay, so ChatGPT generated a problem for us. So this problem, its name is connected components. So you're given on an undirected graph represented as an adjacency list. Write a function to find the number of connected components in the graph. So we have a function called count connected components, and it takes a graph as a parameter, and we have to implement this function. So we have an example graph here, and at the end it should print out the connection between components. For example, in this case 0, 1 and 2 are connected to each other, so this is one connection, and 3 and 4 is connected to each other but didn't connect to the other elements in the other vertices in the graph, so it's another connection. So the total number is going to be 2. So I'm going to stop the video here, and I will implement the function on Python, and I will come back with the answer. Okay, so find a solution for this problem, and I wrote the code implementation for the problem. As you can see, we have two functions. One of them is the function that ChatGPT asks us to implement, and another function called DFS, which is depth first search. So let's see if it's correct or not. Okay, so ChatGPT says that my answer is correct, as you can see, and my function produces 2, which is the desired answer from the function. Now let me explain how this function works and how I implemented it. Before moving on, let me show you the adjacency matrix representation of our graph. So in adjacency matrix, we are putting 1 to the connected vertices. For example, in our graph here, 0 is connected to 1 and 2, so these are the neighbors of 0. So we put 1 in the column of 1 and in the column of 2 here. And here 1 is only connected to 0, so we put 1 only in the place of 0 column. But I accidentally put 1 here, but 1 and 2 is not connected actually, so sorry for that. So and then in 2 is connected to 0, the column 0, and 3 is connected to 4, and 4 is connected to 3. So we put 1 to the connections between the vertices, and we put 0 to elsewhere. And here's the graph representation of our problem. So 0 is connected to 1 and 2, so these are the neighbors of 0, and we have other vertices 3 and 4, and they are connected each other and in here. So since this is an undirected graph, there is no arrows that shows the direction of connections between the vertices. So this is our adjacency matrix and graph representation of our problem. Okay, so now let's move on to our function. So I wrote it on Python and PyCharm IDE, as you can see. So we have two functions, as I mentioned before. So the first function, which is count connected components. So this function counts the total connection between components on a given parameter, which is a graph. And we have a DFS, which is depth first search algorithm, and it takes 3 parameters: graph, vertex, and visited. And we have an input graph, which is the example that is given in our problem. So this graph actually a dictionary in Python. So these keys are the vertices of our graph, and the values of the keys are the the neighbors of the vertices. So for example, 0 has 2 neighbors. Okay, 0 has 2 neighbors, as you can see, 1 and 2. And 1 is only have 1 neighbor, which is 0. And 2 has only 1 member, which is again 0. And 3 has only 1 neighbor, which is 4. It's only connected to 4. And 4 is only 1 a neighbor, which is 3. So this is the main components of our algorithm, and at the end we are printing out the number of connected components. Okay, so now let's see the components of our functions. So in the first function we have an empty set called visited. So this set keeps track of the visited vertices in our graph. And we have a variable called components. So this components variable is initially 0, because we have by this components variable we are actually counting the connection between components, and at the end, as you can see, we are returning it to the user. Okay, so for vertex in graph, so we're actually we are looking for the keys in this graph dictionary. So if vertex is not in visited, we are incremented components by 1, and then we are calling depth first search algorithm. So I'm going to explain depth first search algorithm later. And why we are incrementing components by 1 when the vertex is not in visited set? Because at the beginning of a graph, when we are using a depth first search algorithm, before using a depth first search algorithm, we are counting all, we are assuming that all of the vertices are unvisited. So when there is an unvisited component, unvisited vertex, what does this mean? For example, in our graph, let's say we are started from 0. 0 is initially not visited, so it's unvisited. So where we can go, we can visit 1 and 2, right? So we can find out new sections, we can find out new connections. So this is what does this mean. So but when we come back after visiting the nodes 1 or 2, we are starting from 0, and by the depth first search algorithm we have to move to the neighbors of that vertex. So we have to move 1 or 2, and let's say we move to 1, and when we move to 1 we have to visit its neighbor, which is 0, and when we go back to 0, it's already visited. So there is no new thing to explore. So we have visited 1 also. So if we ever come back to 1, not in this particular problem, but when we come back to 1, it's already visited. So there is no new connections. We cannot find out new connections. So there is no need to count connected components. But when we move to 3, we have to increment it by 1. Why? Because we haven't visited it yet. So we have a connection. We found out a new connection. And then we move to 4, which is the neighbor of 3. And when we move to 4, we haven't visited it yet. But when we move to 3, as you can see, this vertex is already visited, so there is no new connections can be found. So that's why we are incrementing components by 1 each time when we have found a vertex that hasn't visited. So and then we are calling depth first search algorithm on graph vertex visited parameters, and then at the end we are returning components. Okay, now let's move on to our DFS algorithm, which is depth first search. So in depth first search algorithm, so we are getting a vertex from the function count connected components, and we are adding it to the or visited set, and then we are looking for its neighbors in the graph dictionary. We are looking for the values of the keys. The vertices are the keys here, and the neighbors are the values of that corresponds to this key variable. So if neighbor is not in visited, then we have to call depth first search algorithm on it again. So now let's see it for our example. So let's move on to our beginning of our function. We have called a count connected components function. At the beginning we are created a set called visited, and we have created a variable called components. And for vertex in graph, let's say we are starting from 0. So at the beginning we have said that all of the vertices are unvisited, so 0 is not in visited set. So we are incrementing components by 1. Okay, now components is by 1, and then we are calling depth first search algorithm on our vertex 0. So at the beginning of the depth first search algorithm here, we are adding 0 to our visited set. So 0 is added to the visited set, and then we are looking for the neighbor of the graph vertex. We are looking for the neighbors of 0. So we have two neighbors, which is 1 and 2. Now let's see it for 1. If neighbor not in visited, so 1 is not in visited, so we haven't added it to our visited set, so it's not in visited. So we are calling depth first search algorithm on it, and we move on to the beginning, and we are adding 1 to our visited set, and then we are looking for the neighbors of 1, which is only 0, but in this case we are looking for if it is in the visited set or not. It's in visited set already, so we are not going to move on. And then we have to move to the next neighbor of 0, which is 2. And if neighbor not in visited, so 2 is not in visited set, so we are calling it or depth first search function on our neighbor, which is 2, and then we are adding it that vertex to the visited set. We added 2 to the visited set, so totally 3 elements of our graph are added to the visited set, and we are looking for its neighbors. The only neighbor of 2 is 0, and it's already in visited, so we are not going to continue on it. So we are done with the first iteration of our for loop in count connected components function. Then we are going to move to the next vertex. So next vertex is 1. So here we are checking if 1 is in visited set. Is it? Yes, it is in visited set because we have added it to our visited set previously in our previous depth first search call. So this for loop iteration is done, and then we move to the next vertex, which is 2, and if we're looking for if it is in the visited set or not, it's already in visited. We are added it also in the previous calls. So we are done with the iteration 3, which is 2. So then we are moving on to our next vertex, which is 3, and we are checking if it's in visited or not. It's not in visited, right? Because we haven't added it to the visited. We haven't visited in depth first search because there is no connections between the other 3 elements and 3. And then we're calling depth first search algorithm on 3. So we are adding 3 to the set visited, as you can see, and then we are looking for its neighbors. The only neighbor 3 have is the 4, and 4 is not in visited, so we have to call it on depth first search algorithm on 4, and we are adding visited set we are adding 4 to our visited set, as you can see. And then for neighbor and graph vertex, we are looking for its neighbors of 4, which is 3, and we have already added 3 to the visited. So this is done. So we are done with 3, and then we move to the next iteration on our for loop here, which is 4, and we have already added to visited set, so there's no need to continue. So what we have done, we are counted the components and we are incremented it by 2. So our function is going to return us 2. As you can see, it turned as 2. So this is basically all about our function and how it works. Okay, so now I'm done with the homework 7.